I'm a little scared to talk.
Yeah, but do you need to do like an A/B checking for?
Don't do that.
One of the presenters, I feel bad because I wanted to have it. You want to check? Are you session 1 or 2?
Session 1, I think it's session. Yeah, that's the okay. It has this is the latest one.
We can also go to here. Oh, not what I wanted.
Maybe it is. Let's just check that. Maybe.
Oh, check this really quick. So is it this or the one below it? Or?
9:42. Okay, that is yesterday. Is that right?
Is this look?
Yeah. Okay, can you go to the last? Okay. Yeah, I think it was okay. Yeah.
This is good?
Yeah.
Okay.
It's a little like in the shadow. Yeah, by like
There's still new parts of
Wait, when is that? From like a teaching situation or from So which course?
Yes.
Are you going to be kind of around? I mean,
Thursday, I'm going to be in Washington. I'll be around at all. But tomorrow, I be trying to do my exams in afternoon.
Yeah.
Yeah, it's not everyone kind of there's a couple more people.
Yeah. Oh, I see.
All right, good morning, everybody. How's the microphone handling for folks in the back of the room? Everyone hearing me all right? Okay, great. Thank you so much for being here bright and early this morning. I hope everyone is appropriately caffeinated for this beautiful Tuesday morning in Baltimore. Please join me in welcoming the STScI Director, Jen Lotz, who will be giving us some introductory remarks. Good morning.
Thanks, Michelle. Thanks to all of you for coming here on this gorgeous morning here in Baltimore for this workshop, Language AI for Space Sciences. I want to say thank you to the organizers. Thank you to Michelle Namaka, who led the organization of this workshop in collaboration with ESA and the Astrophysics Data Systems. This is going to be a really interesting workshop. You've got an interesting cross-section of people here in the room today: astronomers, data scientists, NLP researchers, software engineers, and archivists. And we're coming together at a really interesting time. Language AI is an exciting emerging technology. It's rapidly evolving, and it's transforming the world around us. It's not just a new tool for data analysis, it's a new way of interacting with knowledge itself. And unlike many previous computational advances, language AI can impact how we search and synthesize literature, generate hypotheses, write proposals and papers, and interface with archives and data systems. Language AI is one of the most exciting emerging technologies of our time, and it is arriving at a moment when astronomy is more data-rich and information-dense than ever before. We are just a few months away from the launch of the Nancy Grace Roman Space Telescope, and just a few weeks ago, the Rubin Observatory released its very first set of alerts, 800,000 alerts in a single night, right? So today and this workshop is not just about this exciting technology, but wanting to come together in a way that's thoughtful, thinking about the impact of this technology on our field. We want to be able to use these tools to accelerate discovery, but we also want to make sure that we can preserve scientific rigor, reproducibility, and transparency. We want to protect data integrity, authorship, and credit. This is incredibly important to make sure that people get the credit for their ideas and their work. And so one of the goals for this workshop is to not just embrace these tools, but figure out how to do so thoughtfully and in alignment with our values. So proceeding thoughtfully as a field means preserving the essential roles of a scientist and astronomer. We want to make sure that we are asking new questions, being able to make those creative leaps, challenging assumptions, and designing our experiments, as well as building community. Language AI can assist in these things, but it should not replace them. And our goal here is to figure out how these tools, these systems, can amplify our creativity and insight. So this workshop is designed a little bit differently to enable those interesting and challenging conversations. It's not a traditional talk-heavy conference. Instead, it has an emphasis on collaboration, discussion, and experimentation. And the hope is that these conversations will help shape the norms for our field. We're still very early in figuring out what language AI will mean for astronomy and space science, and that makes this kind of workshop all the more important. So, here at Space Telescope, this is very much aligned with our core mission of making sure that we make data and astronomy accessible to all. We support the science operations for the Hubble Space Telescope. We do science and mission operations for the James Webb Space Telescope. We support the Mikulski Archive for Space Telescopes, which has the data not just for those telescopes, but a number of other NASA and ground-based observatories. And as I said, we are just really a few months away from the launch of the Roman Space Telescope, in which Space Telescope Science Institute is going to be the Science Operations Center and the data center for that incredible resource. Language AI has implications for our aspect in Space Telescope's work, ranging from how do we use this thoughtfully for proposal preparation to discovering things in our archive and our literature. This workshop aligns with the Institute's commitment to enable scientific discovery and level the playing field. The outcomes of the workshop will help us guide our policy, our infrastructure, and help set community standards. And if we do this well, language AI will help astronomers and scientists ask better questions, connect ideas, and unlock discoveries that we might not have otherwise found. So again, I want to thank you all for participating in this workshop and showing up here. I think it's going to be a really interesting and exciting couple of days. And thank you, Michelle, and I'm going to hand it back over to you.
Thank you so much, Jen. I have just a few logistics items that I want to go over with you before we jump into this morning's talks. You know, as Jen highlighted, one of the goals of this workshop is to facilitate discussion and debate, and I'm super excited just about the interdisciplinary nature of the folks in the room. I think that's going to really support us learning from each other and sharing our ideas with one another during all of the unstructured time that we've built into the schedule. So this morning, if you're giving a contributed talk, those talks are 8 minutes plus 2. Our chairs will be helping you out with time, which will be visible right there on a clock. So please keep an eye on that as we're going through. We'll do a poster pops this morning, and those posters will be up during the coffee break. Those poster pops will be quick 1 to 2 minute presentations at a very high level of the work of the poster. Also, please today be thinking about if you would like to pitch an idea for our hack sessions. So this afternoon and tomorrow afternoon are set aside for small group project work. And then Thursday afternoon, we will be presenting the results of that work to one another. I'd like you all to be thinking about, you know, do you want to present a hack that's a little bit more on the technical side? Do you want to present a hack that's maybe a little bit on the non-technical side? Would you prefer to join a hack that someone else has presented? As you are pondering what kind of project you might want to lead or what kind of project you might want to join, I'd like you to think about 3 different questions, and you don't have to have an answer to all of them. The first question is, what kind of tool would I like to make? That might be a little bit more of a technical hack, right? Maybe in that case, you're thinking about doing something like, you know, a tool where I could put in the abstract of a paper I just written, and the tool might suggest keywords from the Unified Astronomy Thesaurus, okay? So that's question number 1, what kind of tool would I make? Question number 2 would be, what kind of skill do I want to develop? So there you might not be thinking about something you want to give to the astronomy community, but rather some, you know, new skill or new tool you want to try out. And the final question is, how will I use this time to make the community better? That might look a little bit more like a non-technical hack. I know we have one idea that would be to look at AI and trust and build a white paper. So I want you to be thinking about kind of that full range of things as you're pondering. We will spend the time after lunch developing and pitching those hacks to one another and forming some small groups. But I wanted to give you an opportunity during this morning's talks to be thinking about those. And with that, Kelly, I'd like to hand it over to you to get ready for our first speaker. Thanks, folks.
Okay, thank you so much, Michelle. So we've got a good panel of talks this morning. We've got a few contributed talks, the shorter talks, but first we'll start with Anjali Field, if you want to come on up. She'll start us off with a longer talk, and give us just a second. This is our first time. Oh, great. Do you prefer if, do you want this mirrored, or do you have your notes that you want to be able to see?
I don't need to see the notes.
Okay. I'll let you put it in presenter mode. Okay. Okay, and timer is right there, and I'll give you a 5-minute I'll just wait for you.
Great. That includes question time, right?
Do 25 for you to talk and then 5 for questions. So I'll give you 5 before the end of the term.
Okay, great. Got 5 extra minutes. Okay, I'll go ahead and get started. So my name is Anjali Field. I'm an assistant professor in the computer science department here at Hopkins, and I work mostly on NLP, which these days has been rebranded as AI with text data. And what I'm going to talk about today is some of the work that we've done in collaboration with the Space Telescope Institute here, as well as some broader questions around evaluation. So until recently, the way that we typically built technologies for language processing, broadly language technologies, was around designing specialized models that had very clear and well-defined use cases. So we'd build models for things like question answering, machine translation, text classification. And when we wanted to evaluate if these kind of models would work, it was reasonably straightforward. For text generation tasks, sometimes it could be hard to define a metric, but we broadly would come up with a suite of evaluation metrics focused on, does this model accomplish the task that we built it for, and we evaluate how well the model does along these kinds of metrics. That also meant when we wanted to try to look at impacts of these technology, not just how well does the model perform, but if we deploy it, what impact it might have, we could look at things like combining the evaluation metrics with rates of adoption. And if we want to look at potential disparate impacts, how might this technology have different impacts on different groups of people? The example I have on the left here is, does the model perform worse for Black people than for white people? We look at things like fairness metrics and see how does accuracy vary across different subgroups. But now we're no longer in this era. The way that we build language technologies now is the field has very much shifted towards general purpose models that have highly varied use cases. In many cases, we have the model first, and now we're trying to figure out what it is good at. And what this means is that how we understand model performance and impacts has changed, and it's gotten extremely difficult. So if we want to understand how are these models working and what impacts they're having, the first question is just, what are people even doing with them? And we don't have great data on that. And the second question is, what is the actual performance criteria out of these models that matter? And I'll show you some more examples of that in a moment. So these are hard questions, and I only have, I thought 20, but 25 minutes. And so what I'm going to mostly talk about is a case study that we did in investigating how astronomers evaluated a large language model powered system to try to move towards answering some of these questions, and then I'll kind of speak towards how we might try to generalize this to other settings after going through some of the detail. And something that I'll kind of highlight here is that what we did this project with a very interdisciplinary team. So our people in purple here are kind of primarily on the astronomy side, and people in blue here are primarily on the computer science side. And on the computer science side, we have people both in NLP and in HCI who computer action. And so it was really having like broad expertise in this team that enabled us to be able to do this project. So what did we do to understand usage and evaluation? Well, what we started with is we deployed a retrieval augmented generation system for querying astronomy literature, and we deployed it to the Space Telescope Institute Slack space. And so what this bot looked like is people could post on Slack, and if they agreed to be part of the study and joined a channel where they could interact with our system, they could post a question to the bot. We had a retrieval system that would take this question and use it to retrieve relevant papers from Astrophysics archive. And then we would feed those relevant papers and the question into a large language model, and here we're using OpenAI-based systems, and provide a response back to the user. And when we gave these responses back, they included inline citations, and we also pre-populated them with little thumbs up and thumbs down emojis to try to encourage people to give some feedback on whether or not they liked the response. And we did all of this in a group Slack channel, and so that allowed people to view queries asked by other users and comment on them and generally have discussions about whether or not they thought the model was doing a good job. So over this study, we collected all of this data. We collected the queries, the answers, what the responses were, and what the ratings on the responses from the bot were. And what did we do with this data? Why did we do this? So those questions that we're interested in, well, okay, so what we assume in this study and what we sort of confirmed when we talked to people who interacted with our system is that in practice, people were not really using this in sort of real research settings, really trying to understand the literature, right? Like most of what they were trying to do with an initial deployed system is just try it out and see what they thought it was good at and what it worked and what they liked about it and what they didn't like about it. So that's the structure that we use to analyze the data, is assuming that that's the kind of usage that we have. So what do we think we can learn from this data? Well, one is what might be better ways to evaluate models based on how people evaluated models. We had basically people evaluating the system. So what did they do, and could we try to turn that into a systematic evaluation system? The other thing is that this is really a case study of how to analyze user interactions with AI, and we could potentially do this with other models in other contexts to look at questions under a setting where a model maybe is being used more realistically. So given this background, specifically what we looked at was what types of questions did astronomers use to evaluate this bot for interacting with academic literature? And what criteria did they care about in the responses that the model gave to them? So over the course of the study, we had 37 people interact with the system at least once. That resulted in 368 queries. We ran the data collection for 4 weeks. We left the system running longer, but all of this analysis was based on 4 weeks of data. And I'm pretty sure some of the people who were participants are in the room now. So thank you for your contributions to this work. Then what we did is we took all of the questions that people asked the bot, and we manually coded them. And we did this through what's called an inductive coding procedure. This is a fairly standard method for qualitative data analysis, in which we go through all of the queries. We label what we think the kind of type of query it is, and then we regroup and relabel, and we discuss, and we eventually finalize on a sort of labeling scheme of what's all the categories of queries that we have. And it's entirely driven from the data rather than starting with some existing scheme of question types. We also did follow-up interviews with 11 people who interacted with the system, and some of the results I'm showing you is coming out of those as well. So ultimately, these are the queries that we found that people asked. So kind of unsurprisingly, a lot of people asked what we called specific factual questions. So this was just like a straight kind of has a short answer, checking does the model respond with accurate information. But we also had a broad range of other types of things that people asked. So some of the ones that kind of surprised us was a good number of people engaged in some kind of stress testing. So we had directed the system not to answer questions that were not about astronomy. And there are some people who tried to game that and get it to answer off-topic questions. There also was a category of people of questions that focused on asking explicitly hard or unsolved problems in astronomy, and broadly trying to look at how does the model respond to something where there's no clear right answer and there should be a nuanced response. So this is a figure that I really like, which is showing all of the queries. This is our entire data set. It's all of the queries in this study. And what I think the broad takeaway from this figure is the color coding here is the same as on the previous slide. It's by what kind of query the person was asking coming out of our inductive coding. And what we can see is that these queries, this was not it's not like one person asked all of the stress testing and one person asked all of the unresolved topic questions. Like broadly, a lot of people use different kinds of queries. Categories were scattered across different people. And you can see, there was things like people would ask like similar types of questions in a row sometimes, or do huge variance. And one of the other things that we coded here is the open shapes indicate when someone re-asked the previous question. So you get these sort of sequences where someone asked a first question, and then they re-asked the same question, rephrasing a bunch of different times to see how that changed the answer. So most of what I'm focusing on here is really about what people did with the system rather than how the system performed. But we did some analysis of the thumbs up, thumbs down rating. And I'll just show you one piece of that I thought was particularly interesting. So one of the consistent patterns that we found here is that the model's responses to queries from younger, which strongly correlated with more recently graduated users, tended to be rated more positively. So when we start thinking about like how does this model perform for different groups of people, we can't really draw too much from just looking at these sort of ratings. But I think this is sort of interesting tidbit for things we should look at more in the future, is how are models performing differently for different people. Ultimately, what we synthesize out of this is what criteria should we evaluate for models in this kind of context? And so some of this is coming out of our query analysis, some of this is coming out of the follow-up interviews. But one of the questions that we looked at is, broadly, when people were doing these kinds of ratings or reading responses from the model, what did they actually care about? And as you can imagine, one of the first things that people cared about was really just the general correctness, like, is the model factually accurate? But there were broad notions of correctness. So some of this was just straight kind of terms and definitions, but also things like, since the model had a retrieval component, did it retrieve good papers? Did what the model attributed to a paper actually match what the paper said? And these were sort of more nuanced notions of correctness. One of the other things that people cared a lot was around model uncertainty. And this was something that came up as specifically a science setting, where people said, this is a scientific context, and what we train our students to do is to understand how to deal with uncertainty, and when you have unsolved problems in a discipline like this, recognizing that one successful experiment doesn't necessarily mean something is solved, and models just output very confident sounding answers without capturing that kind of nuance and uncertainty. So what we kind of propose here is that if you wanted to go forward from this and actually try to evaluate a model along these kinds of criteria, you need to use a range of different types of queries in order to evaluate the model. If you're only asking the model like specific factual questions, which is really a lot of the evaluation benchmarks that we have, they're taking things from like standardized tests and seeing how models can do on those exams, you're only capturing this really narrow range of correctness, and you're not able to look at these other criteria that people care about. So we stopped short of actually quite implementing how you would do this, but we do give some speculation about how could we implement evaluation metrics that would capture this kind of criteria. The last thing that we do, and I sort of mention this because I hope it might be useful to people in this room, is we took queries out of this data set, and we had astronomers go through and write what do they think is the actual correct answer to this query, manually go through and find the right citations. And so we built like a gold standard valuation data set around answering questions related to astronomy, where your answers are drawn from the literature. And it's not that large, it's about 40 questions, but potentially could be useful for helping evaluate in a future context. All right, so what did we synthesize out of this analysis of user data? Well, we started with identifying evaluation strategies and criteria. As I mentioned, this was also kind of a case study of how we could analyze real usage data. But some of the downsides of this work that we did is it's a fairly limited use case and a small user set. So could we actually do this in another setting, and particularly a broader setting where we have more people and generally a larger context? And there's a couple of things. I mean, there's a fair number of challenges to that, but there are a couple of things that I think are noteworthy that we did that are quite hard to scale. So one of them is that we manually coded all of the queries, right? We had 368 queries, and so we did this inductive coding process, and even with that relatively small amount of data, that took us weeks, right? A second challenge is around privacy and consent, and I'll come back to this in a moment. But what can we do about this inductive coding process? Can we actually do this in a way that's a little bit more scalable? And we did a follow-up project where we designed a method to be able to do this kind of inductive coding process automatically at scale. And we call this high code. And my student came up with tagging the model with this emoji, and I really like it, so I included all my talks now too. All right, right. So as I mentioned, we did this inductive coding process, and how could we scale this? So the pipeline that we came up with is broadly relies on multiple rounds of LLM prompting, and particularly targeting this task of inductive coding. And so what we start with is given some archive that we want to analyze and documents from the archive, and in this example, that might be something like user query data. We provide an LLM with a prompt in which we give it some background on the task that we want to accomplish. We give it the sort of end goal. So in our case, what we were studying was what type of query was this? Was this a specific fact query or a knowledge probing kind or a deep knowledge kind of query? So we give it some goals of the task. and some things like how to format the outputs. We run this initial model across the entire data set and generate labels for everything in the data. And this is kind of quite similar to what first pass of humans doing inductive coding looks like, right? We go through and we label the data with whatever we think is relevant. Then what we do is we do multiple rounds of hierarchical clustering, and we tried out a couple of different clustering algorithms here, but ultimately our kind of final system does this through more prompting, in which we take themes that are generated by the model that are similar, and we merge them and group them, and we can do that through multiple rounds until we get a small enough set of themes that we're willing to look at manually. And when we do this, and we evaluate this across a couple of data sets in the interest of consistency, I'm just showing you the results on the astronomy data. But when we do this and we compare our approach to a couple of existing methods for exploratory text analysis, we find that it does a better job of recovering the themes when we evaluate on data sets that were originally inductively coded by hand. And something to kind of highlight here is that some of the differences between our approach and some of the prior approaches is that they're not really targeting inductive coding. They're really doing more exploratory analysis, whereas our approach assumes we're sort of guided by some research question, like how did people evaluate the model, and that we want our labels to be reflective of that question and not just sort of broadly trying to capture anything that might be in the data. I think these evaluation metrics are not that informative, but what is kind of more useful is to just actually look at what did our model do over this data set. So on the left side here, we have the human-generated labels that we did, and on the bottom we have the ones that were outputted by the model. And then this heat map shows a semantic similarity score between the theme generated by the model and the ones written by humans. And so we can see that we get some reasonable alignment on a fair number of queries. So one, for example, is like literature and citation requests. This is what was generated by the model, and that's really quite similar to the bibliometric search topic that humans came up with and the bibliometric search topic where we had subdivided those into two different kinds of searches, and model kind of grouped them into one. And we find some examples on the other side as well, where, for example, the model came up with a comparative and analytical queries category, which is sort of related to our broad description common sense. I actually probably would call that closer to deep knowledge, though the semantic score doesn't quite capture that. But broadly, we get labels that look like they're capturing the same sorts of information as what we got out of the data by hand. So I presented this approach as a way of analyzing user query data, but it's not limited to that. We really kind of run it on any text corpora that we want to analyze. So one of the case studies that we actually focused on was analyzing an archive of documents related to the ongoing opioid epidemic. And this was internal company communications that were released out of litigation around the epidemic. So it's this huge, massive archive, and there's potentially really valuable information in there around things like how did opioid manufacturers use marketing strategies to push their products, but extracting that information out of an archive like this is quite difficult and time-consuming and messy, and potentially our method can help with this kind of setting. There's also a nice use case that connects back to this idea of how do we query literature with this original RAG system that we built. So this was a recent paper by one of my colleagues in the CS department in which they, contemporaneously built a somewhat similar system in a classic academic fashion down the hall from each other. But their main use case that they focused on was how do we group scientific literature into a hierarchy where we can use that to help explore and understand what's happening in the field. So this is a way potentially that we can try to do this sort of analysis of usage data at a larger scale without necessarily going through and manually coding all the data. One of the other problems that we have if we try to look at broader usage data is how do we actually access that data in a way that's protecting the privacy of the people who did the querying. And in our study, the way we did this is as a research study with informed consent. So everyone who participated in our study signed a consent form. They agreed to participate. They acknowledged that we were logging everything that they did with the model. And then when we analyzed the data, since it was only under 400 queries, we just went through and manually removed any identifiers. And there were some in here, people very commonly ask the model to generate information about themselves. And so we went through and removed those names from the data. And this kind of process gets hard to scale, and it's harder to ensure that your participants really understand that they're doing a research study and that their information is being logged when you try to do this with a broader user group. And I know this for a fact because it has happened. So there's a data set called WildChat, which some of you may have seen before, that was released by AI2 in 2024. And this is a data set of around 1 million real-world user queries of ChatGPT. And the way that they did this collection is they offered people free access to ChatGPT and GPT-4 in exchange for collection of their chat history. So from AI2's perspective, I mean, they'd like check the boxes here, right? Like they did this as a research study, they had permission, they told people we're collecting your chat history. Nevertheless, some follow-up studies from AI2 showed first that, sorry, animations are backwards. Okay, so first, they did some analysis of the data they collected, and they saw that the data contains PII, including things like names, as well as generally references to sensitive topics that people probably didn't want public. They did another follow-up study in which they actually found journalist queries of asking the model to write articles, and they know these were real journalists because they went out and found published articles that matched the output from the model. And the queries contained information about who the journalists' confidential sources were in writing these articles. So you can imagine that if people really, I would hope, if people really understood what we're collecting and making public all of your chat history meant, they probably would not have put these kind of queries into the model. So we can't just trust this consent process to sufficiently protect privacy if we're trying to do this kind of study at a large scale. So how could we do this? And here I'm running out of time, so I'm just going to broadly say some of the work that we're doing is around how do we better anonymize text data. Some of this is can we generate synthesized data under differential privacy? Can we do more kind of standard redaction approaches? Can we do other kinds of synthesis approaches? And then evaluation in a privacy context, similar to an LLM context, is very hard. How do we tell if we've sufficiently anonymized data? So I mentioned this briefly because I'm happy to talk more about any of this work at the coffee break and such. I also want to mention it because if we ask you to participate in a future study, then I want you to know I can't promise your privacy will be protected. No one can promise that, but I can promise that we're trying to be as careful as we can about it. And so broadly, some conclusions. What are some of the things we need to understand usage and impact of AI? We need to be able to analyze open-ended usage data, and we need to be able to do this with properly protecting privacy. And I'll stop there, and I left a few minutes for questions.
Okay, thank you so much, Anjali. So we do have a few minutes for questions. Yeah.
I'm interested in I'm interested in a lot of what you said. Thank you. That was a very nice talk. And a question about high code. On the surface, it looks like topic modeling. So can you just say a few words on how it is similar and different to that?
Yeah, and I have a slide exactly contrasting topic modeling that I took out, which I'm now regretting. So broadly, what topic modeling is doing is really straight unsupervised discovery from the text data. And so I wonder if I still have it in here. Oh. No, I don't. OK. Yeah, it's trying to just directly discover what we might call topics, which is sort of anything of relevance from text data. And so the two methods that I showed as comparisons against our approach, Loom and Topic GPT, these are both actually explicitly designed to be topic models. And if you look in the paper in our appendix, we show some examples of how the outputs compare. And what you can imagine is for a query like, I don't know, how far away is some galaxy? The topic of that query might be galaxy, but what we're trying to code is this is a specific factual query. And so it's trying to capture something pretty different. And that's like, you know, I don't think that Topic GPT and Loom are bad models. They're just targeting topics, and we're trying to target inductive labels that are specific to the research question.
Can you flash up again the reference?
Yeah, where is it?
Thank you.
All right, Raphael.
Thank you for a nice talk. I want to ask about your interpretation of the models, the performance of the LLMs being evaluated more positively by by people with more recent PhDs. Is this telling us something about the ability to be skeptical about what the LLMs is telling us is outputting, or how do you guys interpret this particular result?
Yeah, so we didn't really try to interpret it in this data. I can speculate there's potentially a couple of things going on. So one is it could be that younger users are correlated with sort of more AI practice and literacy in our data, and so they're just better at phrasing questions in a way that the model was able to answer because they have more practice probing models. So that's one speculation. It might be kind of correlated with general AI experience. Another is it could have to do with the topics that they're trying to ask. Like maybe they're asking questions that are more related to things that this model, for whatever reason, had information on. And then a third is that it could be around how they're actually phrasing the questions, in that has been well documented in sociolinguistics that different groups of people use language differently. And the places where that's best been documented is in gender, that women tend to use different language than men do, and that could potentially influence how well a model is able to respond. So we've actually done some follow-up studies on this, specifically looking at gender. The documentation of language differences in age is not as easy to sort of mimic in the settings that we've been looking at. But yeah, I'm hoping to do more work on this because I don't think that our data set was really conducive to breaking that trend down too much, but doing some follow-up studies where we try to collect usage data and we collect demographic information from users, and then do some more studying of how we see performance variation in other contexts.
Okay, we got time for one more. The set room.
So going back to the inductive coding for the questions, did you, are those, first question is, are those available, like the actual questions and the coding for the 368 somewhere? And also, did you find edge cases where you found it actually difficult to figure out what the coding should be?
Yeah, that's a good question. So we did have some, like the way we did the process is the first approximately 100 queries ultimately were co-coded. Like people independently coded them at first, and then we grouped and rediscussed, and we went through and we decided, like, why is this one? Why is this that one? And then ultimately the rest of the data we independently coded so we could calculate agreement among annotators. And then we went back and looked at where queries where annotators had disagreed, and then we rediscussed, like, what should the label be for ones where people had disagreed. And some of the disagreements we think a lot were driven by the kind of interdisciplinary team. Like some of it is just the astronomers better knew this is an unsolved topic in astronomy, and like our NLP coders didn't know that. But like NLP people were more familiar with looking at like stress testing strategies and these kinds of things. And so that's where some of what we think some of the disagreements came from. The query data is all available. It's also on Hugging Face, and it's in the same organization as this one, but it's linked in our paper.
Okay, if you have any more questions for Anjali, you'll be at coffee later?
Yeah.
Yeah, okay. Let's thank our speaker again. Okay, and next up is Eva Moncheva. And give us just a second while we get this reset.
I can see the clock. This one. No, that's not the first slide though.
No?
No.
Oh, I see. It just opened it to a random slide.
Yeah.
So is this over here?
Yes, perfect. All right, is this working? I'm not sure if it's okay. Great. All right, good morning, everyone. My name is Eva Momcheva, and I'm the head of the data science group at the Max Planck Institute for Astronomy in Heidelberg in Germany. And today I'll talk to you about standards for LLM use in astronomy. Every day when I talk to my colleagues or when I open the archive, it feels like we're in a moment where the very foundation of science is under attack. LLMs and Gen AI are storming the gates of the scientific establishment, and we find ourselves in a battle for the very soul of research. Or at least it feels that way a lot of days for me talking to my colleagues. This is certainly a technology that has taken the community by storm. The data shows that the vast majority of researchers are using it in some sort or other for their research. A recent survey amongst my colleagues at the MPIA showed that 65% of them are using it at least weekly in some sort of part of their research work. A broader survey of scientists across different fields from 2024 puts that number at over 80%. And on the surface, we all agree that LLMs are incredibly useful for a whole wide range of scientific tasks, from formatting citations to drafting science papers to summarizing documents. They're really making our work a lot easier. But once we start diving deeper, things are not so clear. Questions arise. Is it ethical to review job applications or proposals with LLMs, to write recommendation letters? Somewhere in these murky depths, perhaps there's a red line that we should not be crossing, because that undermines the very foundation of our research. So I think we can all agree that the tools are here, and I would argue that these tools are here to stay, but the norms are not. We don't yet have an established set of rules and standards within our community on how these tools should be used within our research. So how do we do science now within this context? Do we need new rules? Do we? Maybe. I would argue that no, we don't. Maybe this is a kind of a risky pitch. I would say that we already do have a set of principles on how science should be done. And so let's use the rules that already exist and extend them to this new technology. Science relies on trust, and it's this erosion of trust by LLMs that makes this moment so destabilizing. So in this talk, I want to propose that by reinforcing 3 pillars of the scientific progress, responsibility, recognition, and reproducibility, we can reinforce trust in the scientific process by using, within the context of using LLMs. So I'm going to talk about each of these pillars in turn, and for each of them, I'm going to propose a couple of actions, some on a personal level that you can implement your own work, and some you can introduce on your institutional or professional society level, wherever you have influence to perhaps push some of these ideas. So the first pillar I want to talk about is responsibility. All journals have a statement somewhere in their author guidelines or professional rules, somewhere that it states that the author or the authors carry responsibility for the content of their submission. Here's an example from the ANA journal, where the statement says that by submitting a manuscript to ANA, the corresponding author explicitly states that the work is original and that all co-authors have read the manuscript and agree with its contents. This is the statement of responsibility, and we have similar statements in all journals, especially astronomical journals, but we also have like an implied similar statement in all professional situations. When we submit proposals, whether grant proposals or observing proposals, I think there's an implicit assumption that you are responsible for the work that you're submitting. In a lot of cases, this is explicit. In ANA and other journals, you have to click a box that you have read these, but in a lot of cases, they are implicit. And in professional context, AI cannot take responsibility of the content of a manuscript and cannot agree to a final draft. This is the responsibility of the researcher. We have been implicitly signing off on these agreements throughout our career. One way to strengthen this pillar in the age of LLMs is to make this implicit assumption explicit. Make the authors explicitly acknowledge their responsibility in all situations, all professional situations, perhaps a checkbox the way we do with code of conduct. It's small, but it provides kind of a small reflective pause that allows you to ask your question, are you responsible for the work that you're submitting, that you will be forcing your colleagues to read and assess? On a personal level, this may look like stopping and asking yourselves a little bit more deeply. Does this reflect my ideas? Is this really my work? Can I reproduce the argument that I'm submitting? To help researchers, to help our colleagues at MPA at least, my colleague Morgan Fueno and I have started developing, oops, what happened? I did press the correct button. Did I press the wrong button?
This button.
Yeah.
Okay, yeah, I don't know. You can just put it back up.
Okay. To help researchers at MPIA assess their level of responsibility in different situations, my colleague Morgan Nfueno and I have started developing this self-assessment framework, which for different situations provides a set of questions that researchers can read and assess their level of responsibility. I'll share the link to this. I'm not going to read it, but I'll share the link to this framework at the end. And I would really love to get your opinion on what you think about this and if this is something that can be useful for others. The second pillar is recognition. Does anyone have to know that you're using an LLM? And here again, we have precedent in astronomy. In 2023, the editor-in-chief for AAS journal, Zitan Vishniak, wrote editorial on the use of chatbots in writing scientific manuscripts, where he recommended that as a tool, LLM should be acknowledged and cited as authors would any other significant piece of software. And did astronomers do this? No, they did not. Out of the 12,000 approximately articles published by the AAS journals in the last 3 years, not even 100 cite ChatGPT, and even fewer cite other LLMs. And why is this? This is actually quite understandable, because in the current climate where we're not sure where LLMs stand in the research process, authors face this credit-blame asymmetry, which is a well-known psychological process, where if you're admitting to the use of LLMs, you will get less credit for your research, but then if there is a mistake in your product, you will get extra blame for not being careful enough. And so in order to avoid this credit-blame asymmetry, I think, yes, we need to push for the acknowledgement of LLMs, but perhaps we need to socialize it. Perhaps at first, we need to make this acknowledgement anonymous, so that authors don't need to be penalized in the acknowledgements of their papers by everybody who reads their paper. But the editors perhaps may still see this information. And we should also not just be doing, yes, I use ChatGPT or not, but we should be doing more detailed acknowledgement of how LLMs were used. Two frameworks that I really like in this context are the AI Attribution Kit and the AID framework, which both allow researchers to build very detailed, kind of nuanced statements of how LLMs was used in their research and how it contributed in different parts of their work. Once we've socialized this, we can then introduce policies, and policies like this already exist. I'm an editor for JOS, and we recently actually introduced a policy like this, and we're focusing on this detailed, nuanced acknowledgement, not just yes or no, I used it or not. On the personal level, you can start doing these acknowledgements now, and I would like to invite all of you in this room to start doing these acknowledgements. I'm going to introduce this for my own group at MPIA in the next the papers that we're writing this year. The last pillar I want to talk is reproducibility. Astronomy is so close to being reproducible. Our journals are open access, our data is public, but reproducing the analysis is never practical or often even possible. And LLMs greatly accelerate the generation of the analysis we already cannot reproduce. So the issue for me here is not necessarily who wrote the code, but what does it do? And here we can increase trust through transparency. I would suggest that we start publishing our code. I think this would be really great. We don't actually have any of the journals in astronomy that require open code. Some policies that I found are actually from biology. PLOS has a kind of pretty loose policies, but PLOS biology, which I'm sorry, I skipped, this is missing on the slide, has a really great policy, so I'd recommend you look at that. And on a personal level, we don't need to wait for the policies, we can start publishing our code right now. So in the end, what about the red line? I think a red line should exist, but this is still something that is very much in flux in the astronomical community. This is something I want to pitch as a hack. I want to gamify this, and my colleagues and I kind of hacked vibe coded a game, the ethical gradient game, that allows us to kind of rank different scenarios and draw where the red line is. It's very kind of vague right now, but I would love to hack on this later this week. So in summary, the real risk of LLMs in research is the erosion of trust, and we can combat that by taking responsibility for our work, being transparent, and making our work reproducible. And perhaps with these steps, we can work with the friendly robots. Thank you.
Okay, thank you for that great talk, Eva, and your hack pitch. We have time for one question. Okay.
On the topic of publishing your code, what do you think about kind of dirty code with not nice, comments and things like this? Like imagining, a graduate student that gets through that first paper, maybe some of their coding strategies evolved with time. We think that the answers are correct to publish, but it would be like another project to package up that code in a way that they feel okay passing it along. I'm not saying this is the right scenario, I'm just saying this is what I see happening a lot of times, and so I wonder, like, what's your guidance on trying to get that kind of code publishable in a way that makes it meet these criteria?
Maybe I have a radical opinion. I'm looking at Eric in the background, but I think published code is better than clean code. Transparency is very important, and if you are expecting to put an effort in every piece of code that makes it clean and maintainable and whatnot, this code will never get published, and I think this is why we are in a situation where code doesn't get published. I think licenses limit the liability of the author of the code, so putting a license, archiving it on Zenado, getting DOI, and citing it in the paper is absolutely enough to publish code. And you can absolve yourself of responsibility for the rest of your days, but this will be there. It will be archived and will be visible for anybody who wants to revisit the analysis and find something about how you did the work. And that's more important than having the code be clean.
And a little pitch for ADS. If you put it on Zenodo, we will link it in ADS to your paper so people can find it, which is great. And then people can get credit for their work. Okay.
I'll be here all week, so I'll be happy to chat with anyone, and I'd love to hear your thoughts about the ideas I shared.
Thank you so much, Eva.
Okay.
Okay, next up we have Shanil Varani. We'll just do a little change-a-roo here.
Beautiful. As presenter notes.
So if I go like this, that should be that. Oh, so if you look.
No, I'm here.
Oh. That is a good question.
That's fine. It's fine.
I'm not used to it, so I'm not sure there, sorry.
Good morning. Astronomy, science, communication stories carry authority. They shape and inform the public about black holes, dark matter, discovery of new planets around nearby stars, and of course, the future of space exploration. These stories can now be generated by large language models. The burden of trust doesn't disappear, indeed it increases. In an era when misinformation spreads at the speed of light, how can content creators convey to their followers that their science is correct and independently corroborated? AstroVerify is the Astronomical Society of the Pacific's attempt to build a trust layer for AI-generated astronomy narratives. It is a structured review process that content creators can submit for verification. Upon review and passing a scientific review, a dynamic certification hologram is given to them to embed in their videos. This hologram is then cryptographically recorded and is a certification event published on a public ledger. The goal isn't hype, of course. It's to build trust and convey to the public that the science presented is accurate. Come on. There's a timer on it. Large language models are now used to script astronomy shorts, narrate space documentaries, and generate visual explainers. But there are three recurring errors that have come up in what we see. There are confident inaccuracies, numbers slightly wrong, but stated with certainty, subtle distortions, oversimplifications that drift into misleading claim, fabricated citations, of course, for references that do not exist. I don't know why it keeps jumping on me. And of course, visual semantic mismatch. The video that's going to load on the right is one that's created by InVideo AI. And this is one of many tools where you can enter a prompt. And this is on IMAP. And it'll generate a pretty good looking video with captions that are readily uploaded. How do you know the content is accurate? How do you convey to your followers that it's passed a scientific check? There's no peer review. There's no editorial oversight, so the AstroVerify fills that gap. It blends two layers, a human scientific review and a cryptographic provenance. First, the scientific review. Every submission is evaluated along 5 dimensions of recurring LLM-generated scientific content. Is accuracy correct? What about the source integrity? What about the clarity and comprehension? And then, of course, that visual semantic alignment, meaning the visuals accurately reflect the scientific claims. On the verification layer, every video is given an SH256 hash. It's issued a dynamic certification logo, and of course, a mint of a public certification record on the Web3 ledger that stores the approval of metadata hash. This creates a transparent, temper-resistant public verification and the ability to revoke certification if necessary. Each certification, this creates a durable, inspectable chain of scientific accountability. By doing so, we solve 3 problems. It introduces visible validation. A viewer can verify that a video's scientific claims were reviewed. Second, it creates a durable provenance. Certification events are public recorded and cryptographically anchored. Third, again, as I said, it allows revocation. Trust isn't permanent. It is conditional. As this program grows, we envision a shared community rubric, collaborative governance models, and perhaps expansion beyond astronomy into other scientific domains. If LLM-mediated storytelling becomes a central mode of public engagement with science, then structured trust mechanisms must evolve alongside it. So this program enables the public validation of AI-generated science narratives, durable provenance for scientific storytelling, transparent revocation when standards fail, and a scalable model for community governments. If AI becomes a co-author of the stories we tell about the universe, then we must ensure those stories remain scientifically trustworthy. Thank you.
Thank you so much. Do we have any questions? Yes, John.
Yeah, thanks for introducing this. One of the questions I have is on, peer review itself, which kind of is in a moment of crisis. It feels like it becomes extra load-bearing in this particular formulation. Could you say a bit more about that?
It's the heart of the program, right? In this case, what we are worried about is getting overloaded with submissions. And so initially in our beta testing, it is a human review, and we have those 4 or 5 dimensions that we want to check on. As the program grows, then maybe we can leverage other mechanisms.
Do you envision incentives for gathering more peers? peer reviewers?
Reviewers, absolutely. One of the things we thought about is maybe a discounted program. Faculty can use the program for students that maybe you want to create their own scientific misconception videos, and then of course put it on TikTok or other platforms. Again, that logo conveys authority, right? It conveys that the science is correct.
I'm just curious about the workflow. If somebody submits material, is it equivalent to like peer review for a paper that you currently have editors and then they assign it to a domain expert to review it and then they have a couple different evaluations? Or?
So as of right now, the ASB has a small education team, and so those videos are assigned to the education team, and it's assigned in a way where one of them feels comfortable reviewing it. Again, as the program grows, we want to have a board and have expert reviewers for specific videos. This is all new, right? There's nothing like this. So it's really an experiment. We're trying to see what comes out, but that's the plan.
So it's a great idea. There are many videos though which are false and they won't have this, but people won't know about that.
Yeah.
What copyright issues are involved if someone wants to put not astro-verified hologram on those?
And use their own or copy it from someone else's video and put it on theirs?
Right.
Well, so in that latter case, that's exactly the point of making sure that the logo is public on a ledger, right? Because you can now go to that public ledger and see who was issued that logo. And if it's not the person that's showing it, it's false.
No, I was also talking the other way around. So if we wanted to put this is not verified, this is false on someone else's video.
Oh, somebody else. That is almost, I think that burden would be on the platform host, right? There are so many videos.
Exactly.
Yeah. So this is the inverse problem, right? Because if you want to convey, maybe you have a professional channel, right? And you still want to convey it because the reputation is independent for those people that listen to it. You can use a logo like this. So it's the inverse of that, but you're right.
Okay, I think we're out of time for questions. Let's thank the speaker again. Okay, and next up we have Sanjeev Sharma.
Maybe I can just get it to maybe cancel and then do the slideshow. It's not.
It doesn't do anything.
Is it anything?
Yeah, none of it. It makes a noise.
Oh, here. Well, okay. Cool. And so the forward and back. Okay. Okay, so I'm going to talk about learning to reason with LLM models for technical astronomy tasks. This is a work in collaboration with John Wu, and we are at Space Telescope. So LLMs are great, but I think LLMs with reasoning abilities are a game changer. This brought a fundamental shift in the way we use LLMs to do complex tasks. And this is also what makes AI agents so successful. But to train the AIs to reason, what you need is reinforcement learning, and which requires in turn verifiable rewards. For certain problems, it's easy to verify it than to solve it. And this is like puzzles, playing games like Go, chess, and also doing maths and coding if you think about it. And that's the reason LLMs had a lot of success in maths and coding. But why not develop reasoning abilities in other areas of science like physics and astronomy? And to do this, what you need is you need easily verifiable benchmarks, because unless you can measure performance, you cannot improve it. And it's slowly starting to happening. So the desired properties, like I said, easily verifiable should be one. So that means you can't have open-ended questions. And the other thing is it should be realistic. It should be representative of the actual work done by a typical scientist. Some good ways to generate such question-answer verifiable pairs is to, in astronomy, is to look at technical documentation, where you have survey documentations, instrument reports, data set descriptions, or even softwares. The other good thing is to look at the methods section of astronomy journal articles to see how something was done and you want to reproduce it. So when you want to generate questions from a research article, there are two approaches you could take. One is like the reading comprehension approach, where you say you're trying to generate a question that tests the understanding and the use of the information that is presented. Or the second approach is like you do with graduate students. You say, okay, this is a topic you're interested in. Here's a research paper. Why don't you reproduce the results of this paper? And that's the approach that we take here. And the skills we want to test on is like, can you translate an astronomy and physics concept into a Python code, for example, do mathematics, derive equations, choose appropriate tools to solve a problem, like statistical techniques, computational algorithms, or even Python packages. And once you've chosen a tool, can you use the tool properly? Do you understand the API specifications or even the schema tables of different tables in databases? So the idea here is to create a manually about 100 question answer pairs, because it's a very laborious process, but this will teach us what works and what doesn't work, and you can standardize it and automate it in future. And then we can create a much larger data set of over 1,000 questions. So currently I have 15, and I'm going to talk about my experience with those. And this is kind of showing you the variety of the questions we have. These are mainly based on 3 Roman technical report articles. And we ran Gemini 3.0 both and 3.1 on some of them, and even GPT and the thinking mode of the models. So the questions are like, what is the optimal binning for if you want to do a piecewise constant regression? You have some data with some noise on it. Or think about synthetic photometry. You want to calculate the absolute magnitude in Gaia given the throughput curves of Gaia, and you have a synthetic spectrum. And this problem cannot be solved if you don't know the radius of a star, and the model was actually clever enough to figure that out. Oh, you need to specify the radius. And then you have other science. You can think of a science question, and then you want to make a plot from it. Based around it, and let's say the data comes from Gaia archive, right? And you want to run an ADQL query, you want to process the data, do data processing, and then write a code in Python. Or visibility plots for telescopes. Or think of some mathematical thing like deriving a variance of some complicated quantity, like in near-infrared detectors, you have up-the-ramp sampling and so on. Or you take 2 variables and you want to compute the variance while they have some non-zero covariance, and it can be technically challenging. Or even mathematical equations, and you want to answer science questions based on those equations. Or a familiar astronomy example is like you have a color magnitude diagram, you want to separate giants and dwarfs by some line, but you want that to be independent of, for example, extinction. So I'll focus on 2. I can't go into detail, but happy to talk about them offline. So one is this creating number density map of stars selected with some certain criteria. For example, you want bright stars and having low extinction and having maybe temperature estimates for them. This is for creating guide stars. And you want to know what is the number density of these stars on the sky. And you have to download data from the Gaia archive, and you can't download all the data because all the number of stars are too large. So you want to be more creative, that you want to do all the processing on the cloud. And the script should be flexible enough to, if you want to change the constraints on G and AG, you don't have to download the data again. So if you think about this problem, what you're trying to do is you want to create like a 3D histogram where one of the dimensions is hill peaks ID, then magnitudes, and then the extinction, right? And a typical query would look something like this. You're making use of the Gaia hill peaks function, and then you're doing using floor on magnitude and extinction bins. And finally, you have a group by functionality to create that histogram. Now, there's a lot of logic involved here, like identifying which columns are important. And then once you've run the query, you want to reformat, download the data, reformat it to be able to plot it. And it uses HealPy for doing this. And you also have to convert to densities in correct units. And then also you want to do it in galactic coordinates, so you have to use the appropriate keywords in HealPy. And finally, like the HealPix has two mechanisms, schemes. One is the ring-based scheme, one is and the nested one. And Gaia uses the nested while HealPy has a default of ring. So this is something even I had a lot of time, oh, why the plot is not working? It took me time to realize. But it figured it out that it has to use a nested scheme. With GPT, there was a slight problem. It created a code which was very bloated rather than the much elegant one, the previous one I showed. And also sometimes it makes mistakes in like, it uses the Gaia HealPix index, but it, instead of using source ID as the argument, it tried to use RADEC, just made some assumption. Here's another example, for example, visibility map for the Roman telescope, which will be at L2. So if you think of a telescope having three coordinates, three axes, and there's a constraint on one of the axes, the angle that it makes with the sun line, it has to be in certain range. And based on this, you can say, okay, given a target declination on the sky, given a day of the year, and RADEC, like what's the visibility map? Now, if you use a less capable model, what you find is it makes simplifying assumptions here, and then you don't get the right answer. So to overall, to summarize, this is a small set, but you want to increase it. So most of the problems that we came up with, both the models seem to do a good job. But the scores might look very high, but this is because I used itemized marking. There were lots of reasoning steps to make sure all of them get credit, and there was also soft marking, not really the exact answer, but you got most of the things right. So to conclude, I would say technical astronomy tasks that require complex reasoning and multiple steps can be accomplished as long as the instructions are unambiguous, and there is detailed documentation and worked out examples. So some of the main things to take away are like the positives. I mean, if you look at the reasoning steps that they are doing, you will see that it is trying to do real derivations rather than just memorizing worked out examples. And in terms of the negatives, I think one of the things one has to worry about is the context, the token limits of the context windows, because if you give something that has too many reasoning involved, then what the models try to do is they make simplified assumptions just to complete the task. Yeah, okay, I'll keep up the slide here and take on questions.
Yeah.
So one question I had was, so you have, say, 15 problems or 15 questions that you set out with. So have you tried this where it learns from reasoning on one question and apply it to, say, a second or another question that's closely related? So you assume the reasoning should be about the same. Mm-hmm. So is there a use case for just putting your results towards the next generation for when you do the harder question?
Yeah, so that, like I was saying, it involves reinforcement learning. So once you have a big benchmark, what you can do is you can then say, okay, let's train, because that will involve changing the weights of the models. So you have to train the large language model again. So does that answer your question? Yeah.
I was saying, so how do you capture all that in your runs right now? Like, are you doing it in a way that...
No, so it's not interactive. So it's not learning anything from these questions. So this is right now, the questions are there. We will test, okay, do the models work? And if you find if they are not working well, the idea is you want to come up with harder questions so that it fails. And then you would say, okay, take this harder question, now train a new large language model or a specialized domain-specific model to actually now make sure they work on the benchmark. So that's the idea.
We have time for one more. Eric.
Thanks. This is really interesting. So this simplified assumptions point is one I've definitely encountered before, maybe in less technical settings, but still. Do you find you can get past it by having an extended conversation, or do you really just need to start over or just give up when it makes some stupid assumption?
So since I was in this mode of designing a question and making sure it answers, the format was very different. Normally it would work. I think you can, certain cases, I was able to say, okay, by the way, this is not right, and you make it focus on certain things that I wanted. But in general, I think the approach that would work is, again, like I said, if you can be very clear and make sure that, okay, there's not too many reasons, I'm not giving it too much work, then you have a better chance of getting it right. Or if you're working in agentic mode, like you build a plan, and then you can say, modify the plan accordingly if it's making mistakes there before it does the full calculation. Yeah.
Okay, let's sync the speaker again.
All right, the next two things that we're going to do are some closing logistical remarks and poster pops. And I actually want to switch the order from the one that's on the schedule. Okay. So I want to do the poster pops next. So John, you need folks who are doing poster pops for this session to come on up to the front?
Yes.
All right, please come up if you're doing a poster pop and line up over here. And I think we're not passing the microphone, is that correct? So we'll ask the poster pop presenters to stand here at the lectern. It's fine.
More informal, but also two at a time.
Okay. That were submitted.
Who's names on the schedule and 4 people?
My
on the schedule?
Yeah.
I updated. Oh, I haven't. No, there's no problem. There are 4. Perfect.
We'll just go up to this.
All right. Okay.
Hi, everyone. My name is Adele Plunkett. Very nice to meet you. I work for the National Radio Astronomy Observatory, and one of my primary focuses is our ALMA Science Archive. So my poster is going to have a brief overview of what we offer on the ALMA Science Archive, the interface, the amount of data and metadata that we have, which opens up some interesting data science and AI type project possibilities. I'll show some of the features that we've just added. One is a text-based similarity using text title and abstracts from projects. And then we also have an image similarity, which maybe doesn't directly apply to this conference, but we hope it does, because with the text similarity and image similarity, we're hoping to do a text-based image type search mechanism. So I would love to hear thoughts on that, and if anyone has done something similar, how we can push that forward. In another section of my poster, I'm talking more about prototype projects that we have going to sort of augment features that an archival astronomer can use. And so one of them is a prototype agent focused specifically on querying archival type data from NRAO resources. And it's called Quasar, and it's been developed by a really incredible student working with us remotely. So I'd love to get your feedback on that and see what you think. And then over the summer, we're going to be launching a summer intern program with 3 students through the Cosmic AI Initiative, looking at different pillars of language model implementation with archives. And so benchmarking, infrastructure, including MCP and RAG, and agent development building off of this Quasar tool. So I would really love to hear your ideas. And so come please talk to me at my poster and a coffee break. Thanks.
Hi everyone, my name is Nick. I work at IPAC at Caltech. I'm a data scientist there. and are working on the Exoplanet Archive and Extragalactic Database to develop an AI-assisted tool to accelerate the extraction of data from astronomical journal articles. So we think about this as a pipeline where humans review the tool's outputs at multiple points. This starts by acquiring the articles from journals and then predicting the probability that each article is relevant to the archives using traditional machine learning methods. We then move to identify the names of the objects mentioned within the articles, and for this we found a regular expression search was useful. Next, we move to extract the data from the articles by treating the text and tables separately. For the text data, we use a decoder LLM, and for the tabular data, we break these up and treat them programmatically. The prototype version of this tool has shown significant time savings compared to manual data extraction. However, there is room to improve the recall of the extracted data. One of the main challenges for this is just how different the data are displayed in articles, the different formats that are used. But in order to get around this, we're going to be looking to fine-tune a decoder LLM for this task. Thank you. Looking forward to discussing this more.
No?
That's the wrong Simone.
Okay.
I might have sent you late, so this might be my fault. I'm not sure.
Yeah, but that isn't. Stop hearing. Let's just do that for a second. Nope. I don't have box anymore. Box go. Why is it go? Oh, that's a good idea. Let's just do that. Is that where the other smoke is? No, it's not in there. I think I would have to put a box. Here, why don't I go to...
I have it in my emails if you want me to send this over.
Try session 7.
Yeah, but one second. I also deleted this somehow. Session 7 is which day? Thursday. They don't have that in here yet.
Yes. Missing one?
Yeah. Get the box. Okay, it was in the box.
What's the name?
We have 2 different.
Oh yeah, they were not.
Go to the description.
Mr. Bob. Download.
There we go. Perfect. Thank you.
Hi everyone. I don't know if you remember, but if you were in the first version of this workshop, we did a project in Madrid about studying the use of ChatGPT on astronomy publications. It was basically an idea that came up during the workshop and that I developed as I was an intern there. The idea here, it was like a very cutesy paper. We presented a spice. And the idea, it was the thing that people were doing at the moment. We were looking at words like DALB and seeing if they were present in astronomy publications. And then I got really passionate about that idea, and I started looking into it more. And basically in 2024, there were a lot of papers on this topic, but they all struggled with the way we should actually be doing this. It is that there's something that we feel about ChatGPT and the way it writes. We're like, there's something different from the way human writes, but exactly how do we quantify that? There were 2 main ways of doing it. The first way is that you don't actually use language, you don't actually look at ChatGPT at all. You just look at the papers being published, and you look at the frequency of words across years, and then you look at the difference that come up in 2024 as opposed to all the years before that. You basically fit a linear model on frequencies for each word, and if some are like crazy different in 2024, you're like, oh, okay, that was ChatGPT. The issue with that technique is pretty obvious, is that you're not actually proving that ChatGPT did anything. You're assuming it did, and you're quantifying how much it's doing it. The other way of doing this is you take an existing data set of ChatGPT and human text, so ideally a data set that has ChatGPT written text and human written text on the same topic. You compare those data sets, you extract relative frequencies, and then you look at recent publication in astronomy, and you look again for words that were AI favored, words that AI is much more likely to produce compared to humans. That is also kind of problematic. The first issue is that you're fundamentally changing domains. We cannot actually assume, at least in linguistics, that just because you change domain, things should stay the same just because an LLM changes only the style. That's an assumption that we're trying to prove. We shouldn't start by assuming that. The other problem is that it's actually not very quantifiable. Yes, I can maybe show you a single word appeared more in 2024 and 2025, but I'm not actually proving to you that the text was written by ChatGPT in any actual way. So talking about this issue, I came up with the idea, okay, then maybe we need a data set to study this. And so through UniverseDPT, we created this data set. Basically, we use many abstracts from astronomy. Right now, it's almost like 400,000. And basically, we asked an LLM to rewrite them. And then I now have like this huge data set of human versus abstract on the same exact topics. And now I'm hoping in the following months to actually be using it to study the differences and have a more solid proof of the way LLMs have impacted the language of astronomy. If you have any ideas or any cool things you want to do with data set, come talk to me. I would love to hear from you.
Submit your... Oh, you submitted. Is this the section? Is this okay?
I also submitted a slide, but here's my actual poster. Yeah, so my name is Sarah Burke-Spolauer. I'm normally at West Virginia University, currently on sabbatical at Johns Hopkins until July. If you see me around, come say hi. I'm also currently an AAS publishing scientific editor, and I've been told I'm the only one of those here, so please come and talk to me about publishing ideas and refereeing problems you've had with AI. Meanwhile, me and my student Jordan O'Kelly over in West Virginia are building this database called Bobcat, which stands for black holes, orbiting black holes. The idea is we're putting together a database of supermassive binary black holes, not just the sources themselves, but also the models, so orbital parameters, mass, not just distance and redshift and, position, but, mass, inclination, ascending node, all of these types of pieces of information. Now, we've been working on this manually. This project was posed when we had humans and not advanced LLMs. This field has been rapidly advancing, the field of LLMs, and we recognize that this is ripe for the picking for a tool that can go into literature and extract specific parameters as opposed to us going in and doing it. You can't see it here, but I can talk to you about it at my poster. The information in binary models is stored in plots, it's stored in figure subcaptions, it's stored in text, it's stored in tables. Some of it's internally inconsistent in papers. So it's a tool that's very, needing of an AI development that could go in and extract contextual information from very different pieces of a paper. We're just beginning to explore LLM use on this, a mix of LLM tools and the pre-written tools that we've already made for our own assistance in human extraction, which probably is prone to about as much error as an LLM will be at this point. And that's it. Please come and chat with me about it.
All right, let's thank our speakers and our poster presenters, from this morning one more time. This group has managed to both stay on time and also be active in discussion. So thank you very much for that. What that means is we are getting ready to go into about a 40-minute coffee break. And I hope the discussions will continue during that time. Show me your hand really quickly if you came and there's someone else from your organization who's here as well. So someone else from the same place as you are. All right. I'd like to challenge you during the coffee break not to sit with people from your organization. So find some new friends. There are conversation starters on the table that will be available, so please go talk to someone who you have not met before. Follow up with the poster presenters, follow up with this morning's speakers, and back here at 11:15.
Well, we're doing the photo now.